This will be the final lecture in Chapter 4, Atoms and Elements, and it will cover sections 6 and 7, which are electron energy levels and trends in the periodic table. So section 4.6 is electron energy levels. We need to actually understand the energy associated with electrons when we're learning about how atoms and molecules come together and react, form chemical bonds or break chemical bonds, and so on and so forth, because ultimately the electrons are what are important in these processes. So the first thing on here is electromagnetic radiation, or EMR, and it's all of the various types of energy that exist as waves, and waves are entities that are massless and delocalized. And you can imagine a wave in your head. They have the peaks and the valleys, and it repeats forever. Being massless and delocalized means if you imagine light coming from the sun, the light exists everywhere from the sun and to your eyes, essentially, and everywhere in between. And the wavelengths are repeated with the same amplitude, frequency, and everything ad infinitum. So it's delocalized because it goes literally forever. And the part that makes up the light wave photons, they don't have a mass, but it's essentially these photons in a sea of photons from the sun to us, moving up and down forever. But there are various different types of electromagnetic radiation. There's X-rays, gamma rays, ultraviolet rays, visible light, infrared, microwaves, radio waves, and so on and so forth. All those are the various different types of electromagnetic radiation. Wavelength is the distance between peaks of a wave. It is the length of a single unit of a wave. The electromagnetic spectrum is the various types of electromagnetic radiation that can be arranged based on order of energy or wavelength or frequency. And we will see that in a bit. So as you see here, this image has the electromagnetic spectrum from gamma rays on the right to basically long range radio waves on the left. So here's the gamma rays, and all of these are the radio waves. And it's nice because it shows you the relative wavelength and or frequencies of the type of electromagnetic radiation. So gamma rays, as you can see, have a wavelength of 10 to the negative 11th meters, which is not written in there. 10 to the negative 11th meters. That's 0.000000, too many zeros, 11 zeros. I can't even fit them to where I've written them on there. But I'm going to cross that out. A lot of zeros. Let me try that again over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 1. If the wavelength, which has the symbol Greek letter lambda, is like this, then that wave would be a gamma wave, and it would constitute gamma rays. These are extremely high energy waves. They pass through pretty much everything that you can put next to them. They're extremely dangerous. If a nearby star were to explode into a supernova that gave off gamma rays, I think there's a star that's close by, or Betelgeuse, one of the stars in Orion, I think on one of his shoulders. It's called Betelgeuse. if that one were to supernova, which it is expected to at some point in the future, it would give off gamma rays that would actually destroy Earth because they're so high in energy. It would kill all the life on Earth. And gamma rays are actually used in the food industry to protect some fruits and vegetables so they last longer and have a longer shelf life so they don't go bad before you eat. For example, there's a picture on page 148 in chapter 5 of your book that describes this, where you can see some strawberries that are nice and juicy looking that have been irradiated with gamma rays, and next to them are a couple moldy looking gross strawberries that weren't irradiated with gamma rays. Now it's perfectly safe because it can be done from a distance, so there's no radioactive radiation near these fruits. So it's perfectly safe, and the reason it doesn't actually harm the fruit is because the fruit is already dead, so the gamma rays can't do anything more to it. And if we look at the other end of the spectrum, you can see there's X-rays, which have a longer wavelength than gamma rays, but therefore lower energy. Then you have ultraviolet rays, which have a longer wavelength, but ultimately lower energy than X-rays. Then you've got the visible spectrum of light, which has, again, longer wavelengths, but lower energy than ultraviolet, and so on and so forth, infrared, microwaves, and radio waves. And all the way down here, you have power lines, which run over here with wavelengths of 10 to the 5th meters. So that's, 100,000 of meters for a wavelength that they operate at. Televisions run at tens of meters, which is pretty neat. And AM, FM radios, they operate at hundreds of meters. You might be more familiar with the frequencies that they use for AM and FM radios because FM radios use megahertz and AM radio uses kilohertz. Frequency is measured in hertz. It's not really discussed in your book here, but it's measured in hertz. And so if you have, let's say, 92.3 megahertz, this is 9.23 times 10 to the 7th hertz, which would put it right around here. And so that would be AM radio, or FM radio, sorry. And then the AM radio, let's say you have 1220 kilohertz, this would be 1.22, and it would still be technically 1.22 megahertz, so 1.22 times 10 to the 6th hertz. And so the AM radio is going to be over here. And so the last thing I'd like to point out with this is the bottom part of this picture, where it has the energy increasing for this electromagnetic spectrum going from left to right. And you can see the wavelengths are getting smaller and smaller and smaller, but the energy is increasing.